Okay, so since the audience in the problem for the problem solving session is different from the audience, okay, for the first section of the class, just mute it. Since this is the case, we may have to solve the same problem more than once. So I'll try to solve newer problems first, so that people that attended section 1 of the class not to stay and wait for new problems. So let's start with problem number 11 from the practice test. Problem number 11, yes. Yeah, of course. Problem number 11 from the practice test. Let's see what is there. Problem number 11 from the practice test is, reflection. So this problem is about, it is from chapter, I think, chapter 26 or 25.
It's Mall's law, I think, there.
Mauss's law, yeah. It is Mauss's law, Brewster's angle. So you're looking at a reflection in a pool of water, and you don't see the reflected light when you look through polarizing glasses with polarizing lenses. So you have to recall, I didn't discuss that in detail in the when we talked about polarization of light, but you have to, there is a short statement in your textbook that says that when you have a reflection at some particular angle, so here is the surface, non-metallic surface is needed, and you have incident light at angle theta, you have reflected light, and under some conditions, if the incident light is not polarized, under certain conditions, the reflected light is going to be completely polarized. But you need, the condition is that this angle to have one specific value called Brewster's angle. And well, look, so they're asking about what is the value of this angle. And we're talking about water. So on this side, you have index of refraction of air, which is 1. On this side, you have index of refraction of water, which probably is about 1.33. And you're going to have a complete polarization. So this question has to be stated a little bit. So the person that is observing is right here. So they're asking about either this angle or this angle. It has to be specified. But in order to have a completely polarized reflection of this reflection in horizontal direction, to be completely polarized, you need the following condition to be satisfied. The angle of reflection and the angle at which the refracted light ray comes in has to be 90 degrees. This has to be 90 degrees. This is the condition for having a polarized, completely polarized, linearly polarized reflected light ray, even though the incident light is not polarized. This is the condition. And let's say if you're looking for this angle, it is the same as the angle of incidence. You can say that well, if this is 90 degree, and if this is the angle theta prime, or theta, well, we start with subscript 1 and 2, so this is theta 1 the same, and theta 2 for the refracted light ray has to be theta 2. And from Snell's law, first from the geometry, you have theta 2 is equal to 180 minus 90, right? Minus theta 1. In other words, it is 90 minus theta 1. And Snell's law says, so you're looking for the angle theta 1, for example. So Snell's law says n1 sine of theta 1 should be equal to n2 sine of theta 2. In other words, n1 times sine of theta 1 has to be equal to n2 sine of 90 minus theta 1. So what is it? So there is a trigonometric identity which says that sine of this is equal to, okay, which says that sine of 90 minus alpha is equal to cosine of alpha. A trigonometric identity that is in the books. So knowing that trigonometric identity, you have n1 is 1. I can just say sine of theta 1 is equal to n2 times cosine of theta 1. And therefore, dividing both sides to cosine of theta 1, we get tangent of theta 1, which is the ratio of sine divided by cosine, is n2. And therefore, the angle itself, theta 1, is inverse tangent of n2. Inverse tangent of 1.33. And well, this is going to be this angle. So they're not specifying what angle they're asking about. Are they asking about this angle or 90 minus that angle? But once you have theta 1, you have also this angle, let's call it beta. Is 90 minus theta 1. So one of those two answers should work. Either this one or 90 minus this one should be the answer, depending upon how what they're meaning here.
Where'd you get the 180 from?
Here is 180. So your angle theta 1 is equal to 180 minus 90 minus theta, theta 2 is 180 minus 90 minus theta 1. Right? This is what we have. Here is the vertical, here is the theta 1, here is the 90 degree, and here is theta 2. So theta 2 is equal to 180 minus this minus this. So which one works? This one or 90 minus that one?
The data one is the arctangent of N2.
This one?
And is it because when in the question it says when she puts on a pair of Polaroid glasses with a vertical transmission axis,
So-
is that what it kind of shows that it would be that one and not the other one? Because basically on the vertical axis.
No, so they don't say at what angle she's looking at the pole, what angle with respect to the normal, or what angle with respect to
Okay.
the horizontal. This is, but in optics, the rule is all angles are with respect to the normal to the surface. So they kind of expect this one. So this is Brewster's angle. So theta 1 is also called Brewster's angle. Okay. Okay, so we're done with, this is problem number 11. What is, which, your choice to ask for another problem. So we did some problems here. Let's see which problem didn't we do from the list that is on the board. Did we do problem number 4? Okay, let's do problem number 4 from the practice test. By the way, feel free to ask for questions from the homework assignment and any other questions, any other problems that you may have read in the textbook or in some other book, or maybe some question that, yeah.
Are you dropping one exam or are you carrying all 3?
We're dropping the lowest midterm. Is this what you want or not? Is there anybody that wants we to drop the highest midterm? No? No takers? Okay, so we're dropping the lowest midterm. But still, please, on the final exam, the emphasis is going to be on the last, on chapters that include chapter 24, 25, 26, and 27. And the rest of the chapters are modern physics. So introduction to quantum, introduction to nuclear, particle. You need them, but you don't have the tools to learn real quantum mechanics. So you're going to have some conceptual questions similar to, I'm not even going to put practice tests for the final because we're not going to have the time. We're going to cover the remaining chapters of the textbook except the chapter on relativity. But the questions that you're going to be asked on those remaining chapters are questions related with spectral lines and conceptual questions about hydrogen atom or similar. Conceptual. No much calculations needed at all. Oh, we're going to have actually, we're going to have on one of the chapters in modern physics, we're going to have carbon dating. And for carbon dating, you're going to have a calculational question. Right? Carbon dating is something that works with biological samples. So carbon dating is going to be important, but we're going to solve multiple problems with carbon dating. Okay, so let's do problem number 4 from the practice test now until you come up with other questions. Problem number 4. A dime is placed in front of a concave mirror with given radius of curvature. The image is inverted and 3 times the size of the dime. Determine the distance between the dime and the mirror. So look, they give you that the mirror is concave, therefore positive focal length, and they give you the curvature. So you say that the focal length is the radius divided by 2 with positive algebraic sign. So it is going to be 0.15 divided by 2 is 0.075 positive. Right? Well, the image is inverted, therefore you have to get HI has to be a negative number. But at the same time, they say that it is 3 times enlarged. In other words, they say that the linear magnification, which is HI divided by HO, well, HI is negative. HO by definition is positive. So this is 3 with negative algebraic sign. Because HI is negative, it is inverted for inverted. But you also know that the linear magnification is equal to negative DI divided by DO. They're asking about DO. And here is your equation. So this is your equation. DI is, well, DI is not given, right? Determine the distance between the dime and the mirror. So let's see. So you have, you can say that DI is equal to 3 times DO. And now the mirror equation says that 1 over F is equal to 1 over DO plus 1 over DI. So this is given, but since DI is 3 times DO, it is 1 over DO plus 1 over 3 times DO. So this is equal to what is it equal to? 3 plus 1, 4 divided by DO divided. Right. And now, it kind of becomes clear. So you can write this as one. Well, you can solve it from here. I'll solve it this unusual way. So let's continue here. Well, you can solve it anything. So here is the equation. This is equal to this. You can solve this equation for DO, right? And this is what you're going to get when you do it. Uh, 4/3 divided by, let's see, DO is, yeah. Yes. Yes, that's right.
Why in your magnification equation, the HI is positive when you aim it to be negative?
So HI is a negative number because they say that the image is inverted.
Right, but in our equation, we left it as a positive HI.
Well, HI is a negative number it doesn't, so HI is a negative number. It doesn't mean that I have to say negative HI minus HI. If HI is negative, HI is going to be positive, right? So it is, this is the right style. You place the appropriate algebraic sign in front of numbers, but not in front of letters. Right. This is the right style to work with. A letter can be either positive or negative or zero. So again, this is the right style from algebraic point of view. Other questions here? Other questions? Okay, so let's see if did we solve all of the problems from the list on the board? So we did 6, we did 4, we did 16, we did 9. Did we do problem number 9? Let's do problem number 9 then. Problem number 9. So this is a typical conceptual question that you can see also. I have seen a problem like this in standardized tests like MCAS. So you have to arrange the indices of refraction. And look, the rule is that when the light ray enters higher index of refraction, it bends to the normal. So this means that N2 is higher than N1. N2 is larger than N1, and this is why it bends closer to the normal rather than in opposite direction. And look, if N3 was equal to N1, the light ray here would go parallel to the incident light ray. But it doesn't go parallel, it is bent away from the normal. In other words, N3 is smaller than N1. And from those two, you say that N2 is largest. N1 is the next, and N3, it is the other way around, right? It is the largest, N2 is largest, and 3 is the smallest. So this should be the correct arrangement. Yeah.
So if it bends towards the normal, then we know that N2 would be greater than N1. So say like N3 was like almost parallel with the normal, that would mean that that one is the greatest.
If N3 were this way, very close, much closer to the normal, N3 would be the largest one. So the larger index of refraction, the closer you get to the normal.
Is the answer for that one wrong? Because it says CC, it should be D. No, it's C. Because he just wrote the signs backwards on.
Oh, the answer is the answer is not given that way. So you can say that. Right. So this and this are the same story. I didn't notice what are the options. Okay, your turn now. I think that we did problem number 9 and we did problem number 17. So the problems on the board are solved for the moment.
Where do you have 3?
Okay, problem number 3 from the practice test.
Yes.
Is it bad problem? How is it? So you have objects for so list image distance for 5 objects. So convex mirror. So look, for convex mirror, the image is always going to be virtual, reduced in size. And I think, right, I think it doesn't matter, but always virtual and reduced in size. So virtual meaning the distance di is always going to be a negative distance. So you need negative distance, and you have three negative distances here. Well, it also has to be, let's see, always has to be reduced in size. So m in absolute value has to be always smaller than 1. But linear magnification m is hi divided by ho, it's defined that way, but it is negative di divided by do. So since since this is smaller than 1 in magnitude, you want di in magnitude to be smaller than do, I guess. So let's see where di is smaller than do in magnitude. Not here. Not here. The only one that works is this one. So remember, convex mirror always virtual and reduced in size. This is what I have.
Go over number 2.
Okay, any questions about this one? Number 2 now. Okay, let's go to problem number 2. Okay, so this is a different type of question. So but you're going to have this type of questions. It is a question from chapter 24. So you're going to have one of those. Problem number 2. Problem number 2. So the incident light is linearly polarized. So S naught is intensity of linearly polarized and linearly polarized in vertical direction, according to what is seen here. So here is the direction of polarization of the incoming. The first polarizer is not going to do anything. It is going to let the entire intensity to go through with no reduction, because the axis of polarization coincides with the transition axis of the first one. The next one, so let's do it using the diagram, because look, in many problems without diagram, it is difficult to figure out what is going on. So use a diagram every time when it is needed. So here is S naught is coming in, it is polarized in vertical direction. And here is the first polarizer, transmission axis, also vertical. Therefore, on this side, no reduction of intensity at all. The next one is at 45 degrees. So you're going to have, after 45 degrees, here is the transmission axis 45. On this side, you're going to have S naught multiplied by cosine squared of 45 degrees. Right, on this
So
side.
just divide by 2.
Yeah, this is going to, cosine squared of 45 is 1/2. So it's going to reduce by 1/2 the intensity. And the next one, and the light now is going to be polarized at 45 degrees, just like the transmission axis. And the next one is at 90 degrees, which means that you have incident light that is at 45 with respect to vertical, and you have transmission axis this way. So you're going to have this angle again 45. So you're going to have another reduction by a factor of cosine of 45. So you're going to have S naught times cosine squared of 45 times cosine squared of 45. So you're going to have S naught times 1/2 times 1/2. So S naught, so what is coming on this side is S naught times 1/4. So 1/4 is transmitted. Yeah. Yeah. Yes.
So I guess in my notes, I have that like we're going to the first polarizer, it's S naught divided by 2, and then the next one, it goes S naught divided by 2 times cosine squared of the analyzer.
So if the incident light were unpolarized, then it is going to be reduced by a factor of 2. But the incident light is polarized in vertical direction. So it is not normal light that comes in here. It is a completely polarized, linearly polarized light. If it were light that is unpolarized, here you would have divided by 2. And this divided by 2 would go everywhere. Right? This is,
And it's only because the light's already coming forward.
yeah, the light is already polarized. The light that is coming in is already polarized, yes.
You switch up like the third angle, so that way like.
Oh yeah, you have to, you can change the angles, but you have to find a problem that has different angles. And in the homework assignment you had problems with different angles. I don't know, I don't remember if the practice test has this type of problems with different angles. Okay, yes. So problem number 13, let's see. Okay, so problem number 13. So you can focus between 0.8 and infinity. What is the normal near point? 0.25. This person doesn't see very well close objects. This means that the person is farsighted, hyperopic eye. Correction of farsighted vision is with converging lenses, positive focal length. So what is the refractive power of contact lenses, not eyeglasses, contact lenses that allow normal reading at 25 centimeters? Well, again, the philosophy here is this. Here is the eye. here is the lens right there at the eye. You want an object that is located at a distance GO equal to 25 centimeters to appear at the closest point where the eye can take it over and see the image, take image. And that point is at the near point, which they tell you is at 0.8 meters. So here is the image, the eye at 0.8 meters, but it is in front of the lens. So it has to be negative. You insert negative algebraic sign. And this is also your near point. Well, your near point is at 0.8 meters positive, right? It is distance rather. But from here, they're asking about the focal length, the refractive power inverse. So you say the refractive power inverse, inverse of the focal length, which is refractive power, is equal to 1 over dO plus 1 over dI. So it is 1 over 0.25 plus 1 over negative. So it turns the sign, makes it negative 0.8. And well, you have to do the arithmetic to see. You're going to get a positive focal length because the lens is converging. So whatever number you get, this is your answer. Because they're asking about the inverse of the focal length, which is diopters.
Just go over really quick in general terms, like when an image is negative versus positive for mirrors.
Okay, yeah. So just a minute, let's see if people have questions here.
So for, is it possible to have negative diopter?
Yes, yes.
And that would be considered nearsighted then?
It would be a nearsighted person, yes.
Okay.
It will be a negative focal length, diverging lens, nearsighted person. Myopic eye. Other questions? Okay, so sign convention for mirrors and lenses. So the tricky part of the sign convention is the focal length. Let's start with mirrors. For mirrors, the focal length is positive for concave, negative for convex mirror. HO is always positive, not going to write it. HI, not HI, but DI is positive if the image is formed behind the mirror, in front of the mirror, I'm sorry. So image in front, right? This is the normal location of the image when you have reflection, right? This, if you have reflection, it is coming in front of the mirror, to the left of the mirror. This is the normal logical place. And of course, you get negative if it is behind the mirror, to the right of the mirror. And last, HI is positive if it is upright, negative if it is inverted. So probably this short list, right? This is kind of logical type of sign assignments. Yeah.
DI convention's opposite for lenses?
For lenses, DI is opposite. So lenses now. Focal length positive for converging, negative for diverging. DI positive if it is formed to the right, behind. To the right, well, to the and negative if it is formed to the left in front of the right. Lenses are transparent. You expect the image to be formed on the other side of the lens because they are transparent. The light goes through. And this is normal. In normal condition, positive DI would mean behind the lens. And the same thing for HI as the mirrors. Positive for upright, negative for.
So then for mirrors, for the convex mirror, you will never ever get a positive DI.
This is what it looks like. Yeah. Always convex mirror, always virtual.
And for concave mirror, you'll always get a real image.
I'm not sure about that. You have no. You have to draw. Depending upon where the object is, for concave mirror, you're going to get either positive or negative. It depends upon the location. Try different locations that you're going to see.
We try to do number 14 next.
Yes. Any other remarks about so far the sign convention story?
You said convex always has a negative DI.
Convex, always DI is positive. Hold on. So for convex mirror, always hold on. So convex mirror always has virtual, always negative. Yeah, always negative. Look, if the mirror is like this, it diverges. Any light that comes in is going to diverge. In other words, it is never going to cross another reflected light ray. Only the continuations, which is abnormal situation, are going to intersect, which means that abnormal means negative DI. Right, this is how I remember it. But well, just use your own way of reasoning. Okay, other remarks, questions? Which problem was you said which problem is next? 14, right? Okay, let's do problem number 14. So you can so 14, number 14 right here. So you have converging lens, they give you practically the focal length. And if you place the object at 25 centimeters, you can see it. Therefore, look here, you can answer without practical calculations, but remember, the image is going to be formed at his near point. And now you have the focal length, positive 2.5 meters. You have DO is they want centimeters, right? So you have to convert this into centimeters. But DO is 25 centimeters. DI is going to be formed at the near point. And it is going to be, well, it is going to be a negative according to the sign convention because it's going to be formed in front of the lens where the eye can see it. So it is going to be negative. Oh, hold on. So the eye is, hold on, this is wrong. The O is not known. Actually, it is known. It is 25 centimeters. So it is positive 25 centimeters, like always. But DI is at near point, and it is negative. So 1 over DI is 1 over F minus 1 over DO. So you have to substitute the numbers, but this has to be converted into centimeters. So from here, F is equal to 1 over 2.5. And you have to multiply this by 100 to get it into centimeters. So this is your focal length. DO is positive 25, negative sign here. You're going to get some negative number for DO, for DI. So you're going to get DI is negative, and you're going to say near point is equal to DI with absolute value, whatever that number is. Hopefully it is going to be one of the choices. Yeah.
So if I understand this right, the image will always be portrayed at the near point for a far-sighted person.
That's correct.
But for a nearsighted person, you use the diverging lens, and the image will be
At the
shown
far
at the far point.
Far point, yep.
Okay.
So far point and the near point are the places where the eye can take over and see it.
Okay, so that's why you put the.
So
image
this
there.
is where you have to put the image.
Okay.
So the second section of the class starts in 5 minutes or 6 minutes or so. So let's have 5-minute break. And if you have, so probably don't stop the recording. Maybe just 5-minute break, and after that, well, if you have more questions and you can stay. Otherwise, everything is being recorded, so you can get the video and look at the video. 5 minutes break.
So. Oh, shoot.
Too much.
I'm starting to get it.
It's so strange.
I think that's the only. Also, actually, I would say index of refraction, so that's. So I got super complicated. Like, so
The basic.
okay,
So that's.
or the light is 5 is great. Just trying to get away.
This is okay.
Oh, yeah. Yeah, you guys get 101 from this now.
It's so
35.
It's like so much.
Honestly.
One over. Bro, can you show me? Because this is retake. 5 centimeters, that makes this, I can really know that.
Honestly,
Because it's like. 1 over. That's.
whatever.
It's that 1 divided by 2.5.
Oh.
Is 4 divided by.
Whatever F is the value
We get this.
and refractive power
And
is.
then 1 divided by.
So,
So I was gonna try to figure out like what's going on.
Oh, those. Oh, yeah. So you get
It's a lot. Yeah, it's a lot. I don't know how you get that.
Unless they're just referencing.
Oh, wait, okay.
They work like-
Yeah.
We don't have to cite all of them on the plan. If we have to cite them, then you
Which is
would have to plan.
This is 1 divided by 0.
Oh, I
So like worried about the things that would actually drive me.
Yeah, how are we gonna get through this?
Oh, it's already. I get it. Yeah. Okay, so 2.5.
Oh, okay, I thought she was saying
What
two, yeah, I was like, how many?
Change it.
Okay.
Okay. It's already. Yeah. So whatever that. Alright.
So.
I think this should be that.
So.
Yeah.
I can't stay.
So, And then they do more practice tests, it seems less and less.
This shows without.
Like the most recent thing we talked about here that I've seen on the test is capacitance.
We're not changing, they change half of it.
So I've only had one practice test that even asked about it. But I've only done one AAMC one, so I'll let you know once I get one of those. They have one free one with a sample test that doesn't get scored, so I'm gonna try to score it myself. And then they have a bunch for $35.
Figures, and they're like, oh, what's he I should just like, okay. Combining it with our shakes and because like I'm pretty decent.
No, it saves you.
Really?
It's mostly chemistry.
Oh, okay.
And it's like a drop of math and physics.
Oh, interesting. That's how
The
I
math
want it
that's in it is pretty much
Yeah,
meant to
I
be
applied
done.
it, I applied it in December.
Yes.
So
That's something bad.
it saves me.
Yeah, no, that other project. I wouldn't stress about it.
I'm not. She made it a lot easier than it was gonna be for sure.
People are.
But I just realized that we have like 2 weeks left and I'm like,
Except he totally said that.
Yeah, and she wants to get it comes for.
Oh, I
We just
know.
have like
He totally said
one
it.
kind of different requirement, and that's how I was just talking about it.
Yeah.
I don't even know what you're gonna do.
I guess we have 3 weeks left because no one does dead week, right?
That was why I wanted to talk to her. Say, they know she goes.
I think it'll just be unique, then honestly.
So we probably have to spend most of the time today solving problems of your choice. Practice test problems of your choice and any other problems. Again, I see that some people were in the first session and they're still here. So probably they probably should have the first choice of problems to be solved. So tell me, which problem do you want to see solved? 6. Anybody else?
Yes.
Okay, let's do problem number 6. Okay, so problem number 6 requires you to recall some results from the first semester, pneumatics of motion along a straight line with constant acceleration. So problem number 6. And let's see what they're saying. They say that initially an object is at 4 meters from a spherical mirror, concave. They give you the radius of curvature of the mirror, therefore they give you the focal length. And at some moment of time, you drop the ball, and they're asking at what moment of time the image and the object are at the same location. So it looks like kind of a difficult problem, but in reality it is not. So always draw a diagram. Here's a diagram with a concave mirror. And here is the center of the mirror, and here is the focal point. From what they say, you deduce that the focal length of this mirror is always half of the radius. For our case, half of the radius of curvature is 0.75 meters. So the focal length is 0.75 meters with positive algebraic sign, because concave mirrors, by convention, have positive focal length. And look, once you have the focal length, you can figure out what they're asking for about. So they're asking you the time interval between between the moment of time when DO is at 4 meters and moment of time when DO becomes equal to DI, and since it is a different location of the object and the image, prime it to make distinction between this 4 meters and what they're telling you. The object and the mirror are on the same spot. Keep in mind that the image and the object are on the left-hand side in front of the mirror. And by definition, when the image is in front of a mirror, DI is a positive number. So you don't need to insert negative algebraic signs here. Well, from this, you can say 1 over F is 1 over DO prime plus 1 over DI prime. Well, since DI and DO are the same, you can say that this is 1 over DO prime plus 1 over DO prime is 2 times DO, 2 divided by DO prime. And therefore, DO prime is equal to 2 times the focal length of the mirror. In other words, it is equal to 1.75 meters. Right? So solving this equals to this for DO prime is going to give you that.
Is it 1.5?
It is 2 times the focal length is 1.5. Yeah, 1.5. Yes, absolutely. 1.5 meters. Okay. So 2 times 0.75 is 1.5. And now, basically, they tell you the object initially was at here at 4 meters. At 4 meters. And it fell with constant acceleration equal to 9.8 meters per second squared to a location where it is at 1.5 meters. In other words, the displacement is what, 2.5 meters. From 4 to 1.5 is 2.5. And now your kinematic variables look like this. Displacement is 2.5 meters. Initial velocity, right? You drop the ball from this spot and it is going to fall with acceleration 9.8. But it starts from rest, so its initial velocity is 0. And its acceleration is positive, is 9.8 positive. They're asking the time, what is the time? In kinematics, if you have 3 numbers, you can determine everything else about this motion. So you need a kinematic formula that connects those 4 variables. In other words, you need a kinematic formula that doesn't include the final velocity. And the kinematic formula that doesn't include the final velocity looks like this. Displacement is v naught t plus 1/2 acceleration times t squared. For us, since v naught is 0, the first term goes away. The acceleration is positive 9.8. So you get displacement is 1/2 times g times t squared. And solving this for time, you get that the time is positive square root of 2 times x divided by 9.8. And this should be x. So x again is 2.5 meters. And the optics part of this question was figuring out this displacement x. I see questions and remarks about this problem. Okay, if not, yes.
And G represents the gravity constant.
Yes, acceleration due to gravity.
Okay.
9.8,
Meters per second.
yeah, meters per second squared. Yes.
We do number 15.
Okay, problem number 15 from the practice test. Okay, so this is a problem from chapter 24, and in a sense, it is a practical problem. So they tell you the brightness of a light bulb. Well, they don't tell you that brightness explicitly. They tell you how much energy this light bulb uses, and you have to assume that all the energy that this light bulb uses goes into generation of light rather than heat or something else, which is almost, this is almost the case for LED lights, for example. Otherwise, you have to take into account the infrared component, not only the visible light, but yeah, that's pretty much. So if the light bulb is incandescent light bulb, most of those 150 watts are going to be spent for generation of heat, generation of infrared. But, well, some optical instruments are sensitive to infrared. So, okay, so in other words, you are given the power of your source in watts, joules per second. So intensity, so this is problem number 15. Intensity is defined as energy emitted per unit time per unit area perpendicular to the direction of propagation of this energy. Energy divided by time is power. Divided by area is give you intensity. Now, in this problem, they say that the source emits uniformly in all directions. This means that this power is uniformly distributed along the surface of a sphere with certain radius. So if you take that radius to be 4.55 meters, this is going to give you the surface area of a sphere with that radius. In other words, this is power divided by the surface area of a sphere is 4 pi the radius of the sphere squared. So in this problem, the radius has to be taken to be 4.55 meters, 4.55 meters, because this is the point of interest. This is where you want to figure out the brightness of the light, the intensity S. And therefore, since the power is given, R is given, you can calculate the intensity, the brightness S. So this means that part A is just substitution of the numbers here in this formula. Part A. Part B, you have to recall that for any electromagnetic wave, the brightness, the intensity can be expressed in terms of either electric field, average electric field, or in terms of average magnetic field. So you have to recall, so they're asking about electric field, so you have to use the formula for electric field, which says that intensity of electromagnetic wave is equal to energy density of the electromagnetic wave multiplied by the speed of light. And energy density can be written as epsilon naught electric field RMS value squared. And so this is one way to express the volume density of volume energy density of electromagnetic wave. It can be expressed that way. So knowing this, you can immediately say that RMS value of the electric field is equal to the intensity that you calculated divided by epsilon naught divided by speed of light and under square root. So again, the trick is to remember the meaning of the formula for intensity of electromagnetic wave. And part C is just you to recall that peak value is always equal, peak value epsilon naught is always equal to RMS value multiplied by square root of 2. So just this is important relation to make sense of what is going on here. Any remarks so far, questions about this? Now, in this problem, they can equally well could have asked you about RMS value of the magnetic field of the light. And to find, you just have to remember that the volume energy density can be also expressed in terms of magnetic field. So this also could be 1 over mu naught times magnetic field RMS value squared. And in that case, you would get a similar expression, and you can figure out the RMS value of the magnetic field and the RMS value of the electric field. Also, remember that if you know the value of the electric field in one electromagnetic wave, you can always determine the value of the magnetic field because they're connected. The electric field in normal electromagnetic wave is equal to the magnetic field multiplied by the speed of light. So this is valid for RMS or for amplitude, also valid. Any questions about this problem? If not, let's do another problem of your choice.
Can we please do 10?
Problem number 10 from the practice test. So problem number, yeah, this is a conceptual question that is reasonably easy, but it has to be done. So problem number 10 from the practice test. So to answer that problem, here is the interface between a medium with refraction index NA and the medium with refraction index NB. Here is the incident light ray. And remember that all angles in optics are with respect to the normal to the surface. So with respect to the, if NA, well, if NB is larger than NA, the refracted light ray is going to come here, closer to the normal, getting closer to the normal. Which means that in this situation, you're always going to have refracted light ray, and therefore you're not going to have total internal reflection. So, of course, reflected light ray is always present, but you're always going to have refracted also, light ray that gets in. In the opposite situation, when NB is smaller than NA, you have the following situation. You're going to have, here is the incident light ray. And now the refracted light ray is going to be refracted away from the normal in this direction. If you increase the incident angle, eventually the refracted light ray wants to skim the surface. In other words, at some angle of incidence, refracted light ray is going to disappear if you exceed that critical angle of incidence. So the only possibility for total internal reflection at appropriate angle would be if NB, the second medium, has small index of refraction. So NB wants, you want it to be smaller, and the only case when NB is small is smaller than NA, well, there. So light ray comes from A, hitting B. Well, here you have more than one correct answer. Oh, they're saying when it is not possible. So if you have NB larger than NA, no total internal reflection is possible. And so this is impossible. NB larger means that you're always going to get refraction, and therefore reflection is not going to be total. Some of the light intensity is going to go into refraction, into the second medium. Okay. So it is a tricky question because this is not possible, even though not is involved, I didn't see it. So make sure that you see the things that are in the question. Okay, next. Problem number 16 from the practice test. problem number 16 from the practice test. So you have contact lenses with given refractive power. In other words, they tell you that the inverse of the focal length is 1.724. 1.724 24 inverse meters. Diopter is inverse meter, and it is a positive number what they give you, which means that the contact lenses are converging lenses, which means that the person is farsighted.
Was that converging?
Yeah, yes. Yes. So converging lens because F is positive. This means lens is converging, like this. And converging lenses are used to correct the vision of a farsighted person, a person that doesn't see clearly near objects. So look, a near object, here is the eye of the person, a near object is going to generate light rays that are like this. And they need stronger conversion in order to form an image on the retina. And therefore, stronger conversion you can create with converging lens only. This is how not being able to see close objects, and therefore the person is hyperopic, farsighted. Yes.
So it doesn't have anything to do with like the size of the focal length, just whether or not the focal length is positive?
Well, size, that's correct, yes. So then if it is negative diopters, it is diverging lens. If it is positive diopters, it is converging lens. And now, depending upon how much you want to correct that vision, how bad is, in this case, the vision to close objects, you need different focal lengths, different refractive power. So that's pretty much it. So if the vision is very bad, you cannot see objects that are even as, let's say, at 2 meters. This means that you have to put a converging lens with smaller focal length, which means higher diopters, larger diopters. Well, let's answer this question. Again, all questions that are asking about eyeglasses, contact lenses, it is always a good practice to have a diagram to figure out what is what. And in this case, so we determine that it is a converging lens because the focal length is positive. We determine that the person is farsighted because he doesn't have a problem seeing distant objects. And now we want to figure out what is the near point. So near point, this is the meaning of the near point. The lens has to take the object and create image of the closest location where the eye can take over that image and see it. That closest point is the near point. In other words, here is the eye of the person together with the contact lens right here on the eye itself. Here is the principal axis. So they are telling you that if you place an object at 25 centimeters, 29 centimeters, here is the object at 29 centimeters. From the eye and also from the contact lens. Therefore, DO is 29 centimeters. The image is going to be formed at the closest place where the eye can see it. So the image is going to be formed exactly at the near point. And this is going to be di, which we can calculate it. Keep in mind that it is going to be a negative number because the image has to be formed to the left, in front of the lens, which is unnatural for transparent materials. Right? It is negative number for di, but the near point is going to be at positive distance. So you have to take that into account. And look, so in other words, in this problem, you're looking for di in magnitude. You say 1 over di is 1 over f minus 1 over do, and you have to do the arithmetic after that. So it is going to be 1.724 minus 1 over, oh, this has to be converted into meters if you want to use that diopters. So this is 0.29 meters, 0.29 meters. And this means that when you solve this, you're going to get di to be a negative number, and you're going to get di in meters, which is perfectly fine. And this is, your answer is going to be, near point is going to be your di, but without the minus sign. Because di, the near point is a distance between where the eye can see, the closest place where the eye can see, and the eye itself. Okay, questions, remarks? Okay, other problems?
Please go over 17, Robert.
Problem number 17 from the practice test. So it is practically impossible to solve problems that have the word eyeglasses without drawing a diagram. Don't try, because it is going to be confusing for the grader. And this means that the grader is going to be unhappy, and you know what this results in. So problem number 17 requires no other way. You need a diagram. You're probably, if I'm probably going to give a problem of this type, and part A of that problem is going to be draw a diagram. So this is 17, right? So far-sighted person means, again, converging lens. A near point is given. And you wear eyeglasses that allow you to read from 27 centimeter distance. And you wear the eyeglasses 2 centimeters from the eye. So this is how the diagram is going to look like. It is, here is the lens of the eyeglasses. Here is the eye. Let's make the eye a little bit less like this. Here is the eye. So they tell you this distance, let's say, is 2 centimeters. Here is the principal axis. So you place the object at 27 centimeters from the eyes. So here is the object at 27 from the eyes. And now the image of that object has to be formed at the near point, which is at 48 centimeters. Therefore, the image of that object is right here at the near point, and that distance between the image and the eye is 48 centimeters. Now, looking at this diagram, you determine that the distance between the object and the lens of the eyeglasses, that distance right here, which we call DO, is 48 minus 2, 46 centimeters. You also determine that the distance between the lens and the image, which is DI, is what? So it is, I'm sorry, this is wrong. DO is 27 minus 2, right? This is the object. So the object that the image has to be with different volts, let's say like this. So this is the object. So DO is 25 meters. DI is 46 centimeters. However, it is 46 with negative algebraic sign because that image is formed in front of the lens. If the image were formed here, well, you wouldn't be able to see it, right? Because your eye is. So the eye is negative 46 by convention. Negative 46. And now you can determine the focal length. Right? You have the inverse of the focal length is the inverse of DO plus the inverse of DI. In other words, the inverse of the focal length is 1 over 25 plus 1 divided, actually it is going to become minus 1 divided by 46. So you have to solve this to figure out the focal length in centimeters. It is going to, that number is going to be a positive focal length, which means that the lens is converging as it should be. Again, drawing the diagram is a must.
So if we were given, instead of a near point, we were given a far point, then we would just put the 46 centimeters.
For a far-sighted person, the far point is at infinity and it is not of interest. You're not correcting for distant objects.
But for a nearsighted person,
For a nearsighted person, you need the far point.
right?
So for you,
And so the far point would be in between the object and the lens then, right?
well, find the problem that is asking about far point and a nearsighted person, and we can. It will be a good thing to solve a problem like this. So okay, let me see if we have something like this on the.
I think all of our problems were
There's
with,
only one, and it's kind of, it's an okay problem. I don't.
In the practice test or in the homework assignment? In the homework. Do you want me to do that homework problem?
Yeah,
Okay, let's do the homework problem.
it's the only one I could find that talks about a nearsighted person.
Okay, let's look at it. So.
26, number 4.
Number 4, okay, let's do number 4. Problem number 4 from the homework assignment from chapter 26. For chapter 26. So you have nearsighted person. So you need diverging lenses. So they give you the focal length. You see that it is a negative number, which means it is diverging lens, as it should be. The distance is 2 centimeters between the lens and the eye. And those eyeglasses are perfectly good because they allow you to see objects at infinity, like objects like the moon or the stars and so on. What is the far point? And again, here is the diagram. Diverging lens, the eye, the principal axis. So the diverging lens does the following thing. It takes an object at infinity and generates an image at the far point where the eye can take over and see it. So, object placed at infinity, the lens of the eyeglasses generates an image at the far point where the eye can see it. So let's see. So they say that the focal length is given. For my version, it is negative 486 centimeters. This distance is 2 centimeters. And they say you see clearly very distant images. In other words, if DO is at infinity, DI is created at the near point, at the far point, where the eye can see it. But DI is going to be negative number, keep that in mind. But also the 2 centimeters have to be added. So let's find DI, and after that we have to. So here is the object at infinity. The is equal at infinity, and here is the image of that object. So the object is very bold, make it different from the image. The image is right here at the distance di that we can find. So we find di is equal of inverse of di. The inverse of di is the inverse of the focal length minus the inverse of DO. So DO is at infinity. So 1 divided by infinity is 0. So this is 1 over f. And therefore, DI is equal to f. In other words, DI for my version is equal to negative 486 centimeters. So this is negative 486. And here is the near point that they're asking us to find, from here to here. So you have to take this distance, no negative algebraic sign, because you have to take the distance. So the far point is going to be the distance 486, not negative 486, positive 486 plus the 2 centimeters. So it is going to be 488 is your far point. Yes.
Why is the far point negative in this case, but in the last problem when we were doing near point, it didn't have a sign associated with it?
It was positive. This is why it didn't have a sign.
Oh,
But-
I thought you put it in the absolute value brackets.
Yeah, well, this is, I'm putting absolute value here too.
Oh,
So the far point is equal to the absolute value of di plus 2 centimeters. So the far point is defined as a distance. And distances are positive. So looking at the diagram, to figure out this far point distance, you take 486 with positive algebraic sign, because this is this, and you add this. That's it. Again, the diagram is needed. Without the diagram, it doesn't make much sense. Okay, let's see other questions, other problems from any source, practice tests, or any other source.
So I thought that, okay, so DI, it's with lenses and observing things, it's always negative then?
For correcting lenses and eyeglasses, always DI is always going to be negative, because it is always, the image is always going to be created in front of the lens, so that if the image were created behind the lens, it will be behind the eye and you wouldn't see it.
Okay.
And that image is always created either at the far point for myopic eye or at the near point for hyperopic eye.
So just hypothetically speaking here, could someone be looking into someone else's eyes who they're wearing glasses, like look into their eyes and see the image reflected in their eyes? Would that, in that
So-
sense, would that be a positive DI then?
Well, it depends. You have to give me a more specific question. So you can say, well, is it possible, let's say that standing at the appropriate location, person is typing his password, can you see in the reflection of his or her eyeglasses, can you see his password, right? He's looking at the keyboard, there is a reflection. Yeah, theoretically you can. You can look at the reflection and so on. But again,
We're not gonna have a problem like that, right?
you're not going to have a problem like this. You're not.
So DI is always
But
negative.
actually, you can actually set up a good problem that way. You need, of course, to look at the reflection from the eyeglasses with appropriate magnification, right? Because the reflection is probably going to be small, and from a distance, to see an object that is, let's say, a few millimeters from a distance of 2-3 meters, you probably need to use a
Probably
scope.
have that
A
scope,
scope.
right?
Yeah, you need to. Yes, you need to. But people have. You can put together a question of that type. I'm not going to do it because it doesn't happen that often, right? Nobody is so interested in nobody is so interested in our passwords. Okay, other problems last time? Okay, so I'm going to post this YouTube link, including the link includes the questions that were solved in the problem solving session. And I'm also going to email conceptual questions on chapter 25 and 26. For chapter 24, we found that the questions were not well stated and some of those questions had wrong answers. So I'm not going to send conceptual question file for chapter 24, but you have those conceptual questions in the homework assignment. Okay, so let's end it here. Again, on Wednesday, if possible, attend the test from 11 o'clock session if you can. If you cannot, you come to this session.